Hello, and welcome to the second part of our NASA RSET training on the use of satellite data for air quality, environmental justice, and equity applications. In today's part, I'll be giving you an overview of satellite remote sensing for air quality and focusing on how these data can be accessed and applied to support environmental justice applications. My name is Carl Mallings, and I'll be your host for today's training. I'm an assistant research scientist at Morgan State University, working at the NASA Goddard Space Flight Center through the GESTAR-2 Cooperative Agreement. My background is in civil and environmental engineering, and my work focuses on combining multiple sources of information to better understand air quality at local to global scales. By the end of this training, we hope that you'll be able to identify remote sensing data products which are most relevant to assessing environmental justice issues related to air quality and pollution exposure, and to articulate the benefits and limitations of using remote sensing data to assess environmental justice concerns related to air quality. Before that, though, let's start with a quick recap of last week's training. Based on the review of environmental justice applications for satellite data, which Tanya Kreutzer-Sayed and Ufoma Oviemeda presented in the last part, which of the following categories of environmental justice issues was most commonly featured in the literature review? I'll give you a few seconds to think of your answer. If you picked B, air pollution, that's correct. That was the category that they identified as having the most past work in using satellite data for environmental justice applications. And that's why in today's lesson, we'll be focusing on air pollution applications specifically. To further recap from last week's training, we started off with a general overview of how satellite data have been used to investigate various environmental justice issues, which you saw in the poll, and followed up with some in-depth looks at research investigating nighttime light exposure, drought, extreme temperatures, energy insecurity, and finally air pollution, which is what we will be expanding on today. Across all these applications, you saw how satellite data were combined with socioeconomic datasets to focus on disparities in the negative health impacts of these different environmental hazards across different communities and socioeconomic categories. Broadly speaking, the advantages of satellite data across all these applications include the wide area spatial coverage of these satellite datasets and their long temporal records, allowing both cross-sectional and longitudinal studies. Today, we'll see how this also applies to their use for air quality. However, there are also limitations to using satellite data, including potentially limited spatial resolution and temporal frequency for certain datasets with respect to what might be needed for a particular EJ study, as well as potential discrepancies between what can be observed from space versus what's happening at ground level. Again, we'll see the limitations of these in the context of air quality today as well. So, while last week we got a broad overview of the application of satellite remote sensing data to a variety of environmental justice issues, including air quality, today we'll be looking at satellite-derived air quality datasets in more detail to see how they're generated and what they can and can't tell us about air quality, which will hopefully give you a better sense of how to best use them in your own work. Before I get started, I just want to remind everyone that if they have questions, they should write them into the GoToWebinar question box at any time during the training, and we'll be answering all these questions at the end of the training today. We'll try to get to as many questions as possible live, but even if we don't answer every question, we'll be compiling all the questions and answers into a Q&A document, which will be posted to the training website about a week after the training. So you'll be able to go back and review all the questions and answers there, even the ones we don't get to live. To begin part 2, I want to provide some general background information about air quality and its impacts for those listening today who may be new to environmental justice issues related to air quality specifically, or for anyone who may not have been able to attend last week's training. Globally, poor air quality is recognized as the leading environmental risk factor for premature death, ranking higher than things like poor sanitation and contaminated water. The World Health Organization estimates that exposure to air pollution contributes to more than 7 million premature deaths each year from causes like stroke, heart and lung disease, and asthma. Air pollution and its health impacts are not distributed evenly at a global scale, as you can see in the graphic on the right. Besides these health impacts, there are many other effects of poor air quality, including reduced visibility and reduced yields of crops, which are sensitive to certain pollutants like ozone. Emission of air pollutants is also often accompanied by greenhouse gas emissions, which contribute to climate change. The upside of this is that reductions in air pollution and improvements in air quality can have numerous societal, economic, and climate co-benefits beyond the more direct and immediate benefits to human health and quality of life. To help address air quality problems, national environmental agencies, such as the Environmental Protection Agency, or EPA in the US, as well as international groups like the World Health Organization, have established standards and guidelines relating to air quality, and alongside of these, metrics for measuring and tracking air quality. These metrics typically focus on the pollutants listed on the left side of the table here. These are divided into two groups, aerosols and trace gases, where aerosols are solid or liquid particles suspended in the air. Aerosol pollution is typically quantified in terms of PM2.5 or PM10, or the fine and coarse particulate matter categories respectively. Trace gases considered most relevant for air quality include nitrogen dioxide, NO2, sulfur dioxide, SO2, ozone, O3, and carbon monoxide, CO. The pollutants listed here are regulated both because of their own impacts on human health and the environment, as well as the fact that they can act as tracers or indicators of the presence of other unregulated but still potentially harmful air pollutants. These other pollutants may be co-emitted alongside of, or may form from, or may contribute to the formation of the tracked and regulated pollutants listed here. Air quality standards are based on different concentration levels assessed for different time periods, depending on the relative effects of exposure to different pollutants over different timescales. For example, the US EPA National Ambient Air Quality Standards, or the NAAQS, establish both an annual average limit for PM2.5 of 12 micrograms per cubic meter, averaged over 3 years, as well as a daily average standard of 35 micrograms per cubic meter, representing the 98th percentile of days over 3 years. As you can see in the table, although there are differences in terms of the concentration standards and the time basis of assessment for each pollutant metric, there is a general consensus that by tracking and monitoring these key air pollution metrics, we can get a handle on the air quality situation overall. It's also worth discussing air quality indices when talking about air pollution. Indices like the US EPA Air Quality Index, or AQI, shown here, are basically communication tools used to more easily communicate multi-pollutant air quality information to the public in order to provide guidance about what actions people should take to limit their exposures to poor air quality. In the US, the AQI is calculated for each tracked pollutant on the previous slide, and then the highest AQI value across all the pollutants for which data are available in a given area is the AQI value communicated to the public for that area. The AQI ranges are colored and given descriptions like good, unhealthy for sensitive groups, and hazardous to convey a sense of the general risk. These categories are also linked to specific guidance for different groups who may be more or less susceptible to air pollution's health impacts. It's important to note that for regulation and for research into air quality, we don't typically use the AQI, instead working directly from the concentration measurements. However, for communication with the public, tools like the AQI can be very useful. So, how do we track and measure people's exposure to air quality? As Dr. Susan Annenberg discussed last week, we can do this with a combination of different sources of information as shown here. Typically, nations which have established air quality standards, like the United States, deploy networks of ground-based regulatory air quality monitors to routinely measure the concentrations of the key pollutant metrics. These monitors provide highly accurate data which is needed for the enforcement of air quality regulations. But unfortunately, they also have high setup and operational costs. Low-cost sensors, as the name implies, are a less expensive alternative to these regulatory grade monitors and use simpler and therefore cheaper measurement technologies to measure pollutant concentrations. Unfortunately, those simple technologies are often prone to additional sources of uncertainty. For example, many low-cost sensors operate differently under different relative humidity conditions, which has to be carefully accounted for when analyzing their data. Still, low-cost sensors have allowed for a vast proliferation of air quality data collection, which is giving us insight into air quality in regions and communities which were never monitored before. Because of this, when used appropriately, they can be a very powerful tool for environmental justice applications. However, even taking these low-cost sensors into account, there are limitations in relying on ground-based measurements of air pollution alone. This plot shows the density of PM2.5 monitors per million people on the horizontal axis and the estimated PM2.5 concentrations in different regions on the vertical axis. As you can see, globally, with the exception of some very well-monitored regions like North America, there's usually less than about 10 regulatory PM2.5 monitors per million people, and the regions with the higher estimated PM2.5 concentrations tend to have fewer monitors per capita. The story is similar and maybe even more extreme for other pollutants. Low-cost sensors are helping to fill in this data gap, with some regions seeing up to an order of magnitude increase in the monitoring density when those low-cost sensors are accounted for. Still, there are some clear disparities and data gaps in the ground-based air quality information at a global scale. Zooming into the local scale, we also see a similar picture. Different types of pollution will have more or less variability locally and over short time periods, depending on what their atmospheric lifetimes are and the presence of other chemicals and meteorological factors which affect their dynamics. The plot here shows NO2, one of the more spatially variable pollutants, as measured by a mobile monitoring campaign across the streets in Oakland, California. The star in the center shows the location of the regulatory NO2 monitor for that area. Compared to this single stationary monitor, the local concentrations estimated through mobile monitoring were found to be different by about 35% on average and varied between 2 to 5 times more than what was reflected by the monitor alone. Considering that only about a third of US counties and 60% of US urban areas have even one such monitor, and that the US is one of the most densely monitored countries in the world in terms of air quality, we can start to see the real scale of this ground-based data for air quality issue. So, how can we understand air quality in the absence of local data from monitors or sensors? Models are one very important way of doing this. They are, of course, not measurements of air quality, but rather tools for putting measurements into context and can help us estimate air quality even when we don't have any measurements. However, we still need measurement information in order to calibrate and to validate the outputs of these models. Also, while one modeling approach might be suitable for estimating concentrations at the scales of countries or regions, which is how the regional average PM2.5 concentrations I showed 2 slides ago were estimated, it would take a very different modeling approach to look at the variability in air quality on the scale of a single neighborhood, which was what was shown in the last slide. Given the benefits and the limitations of ground-based monitoring, as well as the capabilities of the different modeling approaches, today, we're going to focus on the role that satellite remote sensing data can have in bridging these data gaps, and especially the capabilities of satellite data when used together with models and ground-based information for investigating air quality in relation to environmental justice. To start our deep dive into remote sensing for air quality, I'm going to be talking about some of the basics of how air quality is assessed from space and tying these to specific requirements of environmental justice applications. A lot of the material I'll be presenting in this part of today's training is drawn from an earlier RSET introductory course available in both English and Spanish using the links here. I'd encourage you to go back and watch those recordings if you want to know more details about what I'll be briefly summarizing in the next few slides. As you heard about in part 1, NASA, along with other international space agencies, operate extensive fleets of Earth orbiting satellites. Many of these have either a primary or a major secondary role of observing the Earth's atmosphere, and in doing so, they provide various kinds of information which are relevant for air quality. Here, I've highlighted a few of the key satellite missions for air quality. Most of the satellites which provide information relevant to air quality rely on passive measurement of the electromagnetic spectrum. This is illustrated in the cartoon on this slide. Basically, as you'll recall from the fundamentals of remote sensing training, light from the sun, including the ultraviolet, visible, and infrared parts of the spectrum, pass through the Earth's atmosphere, reflect from the surface, and pass back through the atmosphere to where it can be detected by a satellite overhead. Along the way, the intensity of the light at various frequencies is modified through interactions with gases and particles in the atmosphere. By taking the measured spectrum of light from the satellite, together with knowledge of what the original solar spectrum was, and applying a retrieval algorithm, which models our knowledge of optics and how light interacts with different particles and gases, we're able to retrieve geophysical quantities, which are basically properties of the Earth system inferred from this indirect measurement of the effect which the property has had on passing sunlight. For air quality applications, we typically consider geophysical quantities like the aerosol optical depth, or AOD, which measures the total scattering and absorption of specific wavelengths of light by particles and droplets in the whole atmosphere. This can be related, using some techniques I'll discuss later, to quantities like PM2.5, which is a measure of the mass of these particles. Other important geophysical quantities are the concentrations of trace gases in the atmospheric column. Many of the commonly tracked gaseous air pollutants, like NO2 and carbon monoxide, can be measured by remote sensing in this way. There are a lot of different properties of satellites and instruments which have an effect on how they can make retrievals of certain geophysical quantities, which have implications for how the data can be used to support different applications like environmental justice. The first property I want to talk about is orbits. Typically, satellites providing retrievals relevant to air quality are in one of two types of orbits. First, on the left, you have a low Earth polar orbit. These circle the Earth north to south and south to north, passing near the poles. As the satellite orbits the Earth also rotates underneath it, giving the satellite a chance to scan across the surface of the Earth. Depending on the satellite and the instrument, you can typically get a complete scan of the Earth every 1 to 2 days, meaning that a satellite will typically see any given point on the Earth about once a day. These orbits are also typically synchronized with the rotation of the Earth around the Sun in such a way that the satellite passes over a given point at roughly the same local time of day, according to the position of the Sun in the sky. So, polar orbits allow you to observe the entire Earth, making about one observation per day at roughly the same local time of day. As Dr. Susan Adenberg pointed out in last week's talk, most current satellite measurements, which are relevant for air quality, are in polar orbits. Geostationary orbits, in contrast, are higher and are synchronized with the rotation of the Earth, such that the satellite is always above the same point on the equator. This means that the satellite will always be observing the same hemisphere of the Earth. This allows for multiple observations of the Earth per day, at least as long as there's sunlight, and depending on the capabilities and the field of view of the satellite instrument. The downside of this is that the satellite will never be able to see other parts of the Earth. We'd need to launch multiple satellites with the same capabilities into different geostationary orbits to cover the entire Earth, and even so, we'd never get a very good look at the poles using this kind of an orbit. So, the satellite orbits have implications for where and when the satellite can observe. This can impact how useful they are for different applications. For example, if you want to research the environmental justice impacts of rush hour pollution using satellite data, polar orbiting satellites might pass over at the wrong time of day for you to do that. Instead, you might want to look into a geostationary satellite and make sure you find a satellite which observes your region of interest, along with the geophysical quantities which are relevant to transportation pollution. On that note, another important factor that plays a role in the types of data collected by satellite instruments is the spectral resolution and range. Spectral range refers to how much of the electromagnetic spectrum can be observed by an instrument, while spectral resolution refers to how well slight differences in intensity at similar frequencies can be distinguished. Instruments providing data relevant for air quality are typically classed as either multispectral or hyperspectral. Multispectral instruments make measurements at distinct bands of the spectrum. These bands can cover a large portion of the spectrum, but each band itself is rather broad, so the spectral resolution is low. In the plot at the right, MODIS, which is an example of a multispectral instrument, is observing at a few distinct bands in the visible and infrared parts of the spectrum, where each band is about 10 to 50 nanometers wide. Multispectral instruments are better suited to measuring quantities like aerosol optical depth, which relates to how much visible light is being blocked by particles in the atmosphere. Hyperspectral instruments, in contrast, have much finer spectral resolution. I have several examples of hyperspectral instruments on the right. These different instruments are covering different parts of the spectrum, but they all have very fine spectral resolutions compared with the MODIS instrument. For example, TRPOMI is a hyperspectral instrument with a spectral resolution of about half a nanometer for its bands, which is nearly 100 times finer than MODIS. What this spectral resolution allows hyperspectral instruments to do is to distinguish subtle differences in the spectra due to interactions of light with different trace gases. This makes hyperspectral instruments much more suitable for providing data on trace gases in the atmosphere. For environmental justice applications, it's important to consider what kinds of pollutants might be impacting a given community and to choose instruments with appropriate spectral ranges and resolutions for capturing information about these pollutants. I also want to talk about spatial resolution. Usually, we consider this using the size of a pixel of a satellite instrument projected onto the Earth's surface directly below the satellite. This is the native resolution or the nominal resolution of the instrument. For air quality applications, better spatial resolution will allow the satellite to better detect differences in the atmospheric column above nearby locations. Finer spatial resolution also gives more opportunities to see past things like cloud cover, which might block a single large pixel but not block parts of a smaller pixels covering the same area. The general trend has been for spatial resolution to improve over time. I'm illustrating that using the nadir pixel sizes from some hyperspectral instruments. You can see how over time, as we moved from GOM2 and Skiamaki and OMI instruments in the early 2000s to more recent instruments like Tropomi and Tempo, we're getting to finer spatial resolution. The same general trend also holds true for the multispectral instruments, although the changes have been a little bit less dramatic. To illustrate the effect which this has had, here are some composites of 1 day of NO2 observations from the higher resolution Tropomi instrument on the left, which you saw in Dr. Susan Annenberg's presentation last week, compared to the older and lower resolution OMI instrument on the right. You can see the dramatic differences which the higher resolution has made. In the OMI image, you can pick out the emissions of a few major cities like Phoenix and Chicago, but they're not so distinct, and there are a lot of missing data, both due to clouds blocking pixels and something called the Rho anomaly, which is limiting OMI's observations as its performance has degraded over its almost 20 years in orbit. With the Tropomi image, you can pick out major cities which are much more clear and distinct in this image, and even distinguish some smaller sources. Even individual highways and power plants will sometimes show up, as you saw in some of Dr. Susan Annenberg's examples last week. There's also a higher spatial coverage, in part because with more pixels, there are more opportunities to see past gaps in clouds. Of course, there are still some limitations to this spatial resolution. Thinking back to the example I gave about the variability of NO2 across streets in a neighborhood, that whole area is still represented by about 1 Tropomi pixel, or about 2 Tempo pixels. So with these instruments, especially from a single scan from an instrument, you wouldn't be able to distinguish the variability in concentrations across this neighborhood. We're not yet at the point where we can observe these street level differences from space alone. The best we can do is to be able to distinguish between larger neighborhoods or urban areas. It's also important to remember that what we're seeing from the satellite is the whole atmosphere above a location. What's happening right at the ground level where people breathe could still be different from what the satellite's measuring. You'd have to start bringing in other sources of information from models, from land use information, and from ground monitoring data where it's available to really get at a quantitative analysis about what might be happening at these very fine spatial scales. So to summarize, what are the advantages of using satellite data in air quality environmental justice applications? I think the key advantage is the wide area regional or global spatial coverage that satellites provide, which can give you the big picture of the air quality situation, including where the hotspots are and where pollution might be moving from place to place. This is vastly more information and better spatial coverage that can be achieved with ground monitoring networks alone, even taking low-cost sensors into account. Secondly, we have the fact that some instruments like OMI have been in operation for many years, observing the same places on Earth every day with the same instrument. This gives us a great data set to look at changes over time, such as how shifts in human activity, like new environmental regulations or more recently the COVID lockdowns, have impacted air quality at a large scale, either dampening or sometimes exacerbating disparities. Finally, the spatial resolution of satellite air quality data has been improving to the point where we can start to see the variability within certain larger urban areas and to look at individual sources like power plants from space, as well as making comparisons across larger regions and between cities. We also need to acknowledge the limitations of satellites. As I mentioned, most of the satellites providing data relevant for air quality rely on sunlight to make their measurements. So in the absence of that sunlight, there won't be any data. This means no observations at night and no observations through thick cloud or smoke cover. This could bias our understanding of what's happening in the areas, especially where there's heavy cloud cover or where the area is frequently covered with wildfire smoke, if we relied on the satellite data alone. Also, as I mentioned, satellites are typically observing the entire atmosphere between the surface of the Earth and the orbit of the satellite. What's happening over that scale may or may not be well representative of what's going on right at the ground level where people live and breathe. Finally, the orbits of certain satellites limit the times of day where they can make their observations, and the air quality situation which the satellites observe at those times of day may or may not be representative of what's going on at other times of day or at night when even geostationary satellites won't be making observations. Let's pause and see if we can take what we've learned so far to answer this question. Say that I want to investigate how gaseous transportation-related air pollutants, like NO2 or CO, might vary in different communities at different times of day. What kind of satellite instrument could give me the data which is relevant to investigating this question? A geostationary multispectral instrument, a geostationary hyperspectral instrument, a polar orbiting multispectral, or a polar orbiting hyperspectral instrument? I'll give you a few seconds to think about that. My best answer to this would be to look for a geostationary hyperspectral instrument. Because I'm looking at how concentrations vary at different times of the day, I need a geostationary orbital instrument to do that. And because I'm interested in gaseous pollutions, not necessarily particle pollution, a hyperspectral instrument is better suited to give me that kind of information. Before I move on to talk about specific satellite datasets and products, I want to talk a bit about processing levels. This is a system NASA uses to identify how much analysis goes into generating different datasets. It starts at level 0 with the raw information coming down from the satellite. At level 1, we use information from the position of the satellite and the pointing of its instruments to reference these raw data to the corresponding locations on the Earth's surface where the instrument was looking. Typically, the level 0 and level 1 data aren't used for air quality applications. Where we start to get more useful data is at level 2, when we apply retrieval algorithms to extract geophysical quantities like the column densities of trace gases, as shown here for NO2. At level 2, the data is still at the pixel resolution of the satellite, which is the highest spatial resolution we can get. But the locations and sizes of the pixels will be different depending on the orbital track and the viewing angle. To make the data easier to work with, we often also create level 3 datasets. These take the level 2 data and regrid them onto a uniform grid in space and time. For example, a latitude-longitude grid over the Earth's surface, with all data collected over a full day being aggregated together to produce one map, as shown here. As a part of this process, we also typically do some quality control, screening out pixels where there was too much cloud cover or where the retrieval algorithm performed poorly for some other reason, in order to get the best possible data quality for the product. Because it's on a uniform grid, the level 3 data are much easier to work with than the level 2 data, and typically we recommend new users to start here when looking at satellite data. The downside, though, is that the regridding reduces the spatial resolution, and different gridding algorithms can produce slightly different estimates for the grid cells. So for applications which need very high spatial resolution, it may be necessary to go back to the level 2 data. We also sometimes go to level 4 data products, which combine satellites and other sources of information, especially models, which allow us to do things like fill in gaps in the data from the satellite, or use model estimates to infer surface level concentrations of pollutants from the atmospheric column information which is being collected by the satellite. Since we're now bringing in other sources of information, which involves making several assumptions, the level 4 data are subject to usually greater uncertainties than the other, less processed data, but these can also be very useful in situations where complete data coverage in space and time is important. I'm now going to give a brief rundown of some important satellite data products which could be relevant for air quality and environmental justice, starting with data related to aerosols in the atmosphere. Because I'm going to be going very briefly through these data sets, if you'd like to learn more about them and how to use specific ones, I'd encourage you to take a look at the other RSET trainings which cover them in more detail. For example, I'm going to be talking about the MODIS and VIIRS instruments first, and there was a recent training explaining those instruments, as well as the differences between them and how NASA is transitioning from MODIS to VIIRS, which is linked on the slide here. So, what are MODIS and VIIRS? MODIS is the Moderate Resolution Imaging Spectroradiometer. It was launched back in the late 90s and early 2000s on 2 satellites called Aqua and Terra, which are both in polar orbits. Aqua passes over in the afternoon, making its observations at about 1:30 p.m. local solar time each day, while Terra passes over in the morning about 10:30. VIIRS, the Visible Infrared Imaging Radiometer Suite, started operating on the SNPP satellite in 2011 and has also recently been launched on 2 more satellites in 2017 and 2022. These satellites are also in polar orbits and pass over in the afternoon between about 12:30 and 1:30. Both MODIS and VIIRS are multispectral instruments covering parts of the visible and infrared spectrum, making them suitable for aerosol observation. VIIRS generally has a slightly higher spatial resolution than MODIS for the bands which are relevant for aerosol observation. MODIS and VIIRS produce several data products relevant for air quality applications. In addition to true color imagery, both produce various aerosol optical depth data products, which are relevant for particulate matter pollution. These different products use different retrieval algorithms, which I'll talk about on the next slide. There are also fire detection products from both instruments, and the VIIRS instrument also has abilities to produce smoke and dust detection information. Here's a side-by-side comparison of aerosol optical depth, or AOD, from MODIS on the Aqua satellite on the left, and VIIRS on the SNPP satellite to the right. Broadly, you can see the areas of higher aerosol optical depth due to airborne dust or smoke in the red colors, while the lower aerosol optical depth over cleaner areas is in yellow. You can also see the interference in aerosol optical depth retrievals caused by clouds and bright surfaces like snow and reflected sunlight from the oceans for both instruments. There are also gaps in the single-day coverage from MODIS due to the narrower swath width of that instrument. VIIRS has a wider swath providing full coverage for a single day. Here's a side-by-side comparison of different aerosol optical depth retrieval algorithms applied to MODIS data. On the left is the deep blue algorithm. This is applicable for land surfaces only and typically works best for bright surfaces like deserts. The spatial resolution of that product is about 10 kilometers. The dark target algorithm provides AOD for both land and ocean surfaces, and as you might guess from the name, it gives better performance over darker surfaces like vegetated areas. There are both 10-kilometer and 3-kilometer versions of this algorithm, although the high resolution version has some known issues with more reflective surfaces, especially in urban areas. Finally, there's the MIAC algorithm, which takes data from both MODIS Aqua and Terra satellites to create its data products. It's the highest resolution product available for MODIS AOD, with about 1 kilometer pixel resolution. We typically recommend MIAC for most work related to air quality, since its high spatial resolution gives it some notable advantages there. However, there is also a processing delay associated with the MIAC algorithm, so if you need a quick data turnaround, another product might be more suitable. For the VIIRS sensors, there are also similar AOD products available with usually slightly higher spatial resolutions. One exception is MIAC, though, which unfortunately is not yet available for VIIRS, although this is something which is being investigated, and we hope to develop a VIIRS MIAC product in the future. VIIRS also provides smoke and dust aerosol index information. You can see in the figure here how the large Saharan dust plumes crossing the Atlantic are being flagged as dust, while there is some smoke being detected from fires in Central Africa and northern Canada. There are also uncertainties associated with these indices, and they should be taken as indications of the possible sources of aerosols rather than absolute identifications of different types of aerosols. But if you are interested in determining the sources of particulate matter, these indices may be useful to you. Now, as I mentioned earlier, and as Dr. Susan Annenberg discussed last week, satellite AOD is related to particulate matter, but satellite column AOD and surface level PM2.5 are very different quantities. There are methods to infer one from the other, however, which typically involve combining satellite AOD with other information from models, as well as surface level PM2.5 monitor data where those are available. Various of these level 4 data products have been developed for surface PM using information from all these data sources put together. Dr. Susan Annenberg presented on some of these satellite-derived data products last week, and here I'm showing another example of such a data product, which is a monthly map of surface level PM2.5 over the United States. There are several different generated data products for PM2.5 such as this, as well as different subsets of PM2.5 like dust or organic carbon categories, which have varying spatial coverage, either global or national, varying spatial resolution, typically 1 kilometer or less depending on the input data sources, and varying temporal resolutions, typically annual or monthly average data, although there are some daily average data sets which have been developed. Because of the data processing that goes into producing these level 4 data products, they typically take several months or even years to create, and so can lag quite a bit behind real time. However, for retrospective studies, these data sets can be very useful. The NASA Socioeconomic Data and Application Center, or CDAC, is a good resource for finding these data sets. While I've been talking about MODIS and VIIRS, which are polar orbiting instruments, I also want to mention geostationary instruments providing AOD data. The key advantage here is the higher temporal resolution available with geostationary instruments. For example, the instruments covering North America are capable of scanning the full hemisphere about every 10 minutes. This makes geostationary AOD very useful for tracking rapidly changing atmospheric pollution events, especially wildfire impacts. Depending on where you are, though, you will need to look at different satellites. GOES 16 or GOES East and GOES 18 or GOES West are the satellites which provide coverage for the United States. Other regions are better observed by other satellites as listed here, and the different satellites may have slightly different capabilities. Some surface level PM2.5 data products are also available using geostationary AOD data. Here I'm showing an example of a daily PM2.5 map over the contiguous US, created from a composite of AOD information from the GOES satellites and surface level PM2.5 monitored data for the US and Canada. You can access these images from the NOAA Aerosol Watch website linked at the bottom of the slide. If you're interested in using geostationary AOD data, I'd encourage you to take a look at our earlier ARSA training on accessing and analyzing air quality data from geostationary satellites, which is linked here. I also want to mention the capability of satellites to provide information about fires, which can be a significant contributor to air quality disparities for certain regions. Various instruments, including MODIS and VIIRS, provide information about thermal anomalies on the Earth's surface, which are most likely due to fires, although there are still some false positives and some small fires might be missed. Furthermore, satellites provide information on fire radiative power and energy, which are measures of how intense a fire is and can be related to its emissions. If you're interested in fire-related impacts for environmental justice, I'd encourage you to take a look at our recent ARSA training on fire risk detection and analysis, which is available in both English and Spanish using the links here. To wrap up our discussion of satellite aerosol data, I want to bring your attention to an upcoming NASA mission called MAIA, or the Multi-Angle Imager for Aerosols. Unlike the other polar orbiting satellites which I've talked about, MAIA will be a targeted mission focusing on several US and global cities as designated on the map here. As it passes overhead, the imager will rotate, scanning each target area from different angles, as shown in the animation. This multi-angle information will allow us to infer various aerosol properties in addition to the aerosol optical depth, including information on particle sizes and composition. A big part of the MAIA mission is also on-the-ground data collection in the primary target areas to validate and ground truth the satellite data, as well as health studies being conducted in these regions, which will try to link the MAIA information about aerosol properties and composition to specific health impacts. This is NASA's first explicitly health-focused mission, and is hopefully going to provide us with some new insights into the links between particulate air pollution and human health around the world. If you're interested in learning more about this mission, I'd encourage you to visit the mission website at the bottom of the slide, where you can sign up for the MAIA Early Adopters Program and learn more about the mission and the data it will collect, and also prepare to use these data in your own work following the launch of the satellite, which is scheduled for next year. I'm now going to transition from aerosols to trace gases. I'll again be giving a high-level overview of the trace gas data products from satellite instruments. If you want more detailed information, I'd encourage you to take a look at our recent training on high-resolution NO2 monitoring using TROPOMI, which also covers some other trace gases and instruments and is linked here. I'm going to focus on the OMI and TROPOMI instruments, which are two of the key missions for monitoring tropospheric trace gases. OMI, the ozone monitoring instrument, was launched back in 2004 on the polar orbiting AURA satellite. This is a hyperspectral spectrometer covering the ultraviolet and visible spectrum with a spectral resolution of about 0.5 nanometer. It provides daily coverage with an afternoon local overpass time. On the right, TROPOMI, the tropospheric monitoring instrument, is actually not a NASA instrument, but a European Space Agency instrument launched in 2017 on the Sentinel-5P polar orbiting satellite. In many ways, it's a successor to OMI with two key advances. It has a higher spectral range than OMI, stretching into the near and shortwave infrared, as well as a much higher spatial resolution, as I showed on an earlier slide, of about 5 to 7 kilometers per pixel for many of its bands, compared to the 13 by 24 kilometer pixels of OMI. It also passes overhead in the early afternoon. OMI and TROPOMI both provide several trace gas data products relevant for air quality. Both provide tropospheric and total column nitrogen dioxide products, as well as total column SO2 and column formaldehyde products. Both instruments also provide ozone data products, although there are some limitations related to these for air quality applications, which I'll talk about on the next slide. Finally, the wider spectral range of TROPOMI allows it to also provide carbon dioxide and methane data products. Regarding ozone, despite its being an important atmospheric pollutant near the ground level, it's very difficult to accurately observe near-surface ozone from satellites. That's because the high levels of ozone in the stratosphere, which is the ozone layer you've probably heard about, tends to overwhelm the much smaller signals of near-surface ozone in the satellite data. Although there are data products which attempt to disentangle the stratospheric and tropospheric ozone signals, at this point, we typically recommend against using satellite-derived ozone information for air quality applications specifically. On the other hand, as Dr. Susan Annenberg showed us last week, nitrogen dioxide is very well suited to monitoring with satellites. Because of its relatively short atmospheric lifetime, it tends to be concentrated near its sources, which include transportation, industrial activities, and power generation, which make it very suitable for investigating surface air pollution, especially in urban areas. OMI and TROPOMI both provide information on tropospheric nitrogen dioxide columns with daily global coverage. OMI provides low resolution level 2 and gridded level 3 data products, which have an almost 20-year record, making them suitable for trend analysis in environmental justice investigations. TROPOMI provides a high resolution level 2 data product covering the last few years if you're more interested in a recent analysis into more fine scale disparities. Despite TROPOMI being a European satellite, through an agreement with NASA, we are able to provide TROPOMI data through our own data access systems as well, which I'll talk about towards the end of the training today. Formaldehyde is another data product provided by both OMI and TROPOMI. While it's not often used directly for air quality applications, it can serve as a rough proxy for other volatile organic compounds, since it is a byproduct of the many reactions which involve these compounds. It's also used together with nitrogen dioxide retrievals to examine ozone formation potential. While we can't observe near-surface ozone with satellites, by using the ratio of formaldehyde to NO2 from the satellite data, we can take a look at whether different regions are in the so-called VOC-limited or NOx-limited regimes in terms of ozone formation, which has important implications about what kinds of policies might be more effective in reducing ozone pollution in those different areas. Again, OMI provides the longer data record for formaldehyde, while TROPOMI provides more recent, higher spatial resolution data sets, with TROPOMI data being available by NASA through an agreement with the European Space Agency. Sulfur dioxide is also a key pollutant observable by satellites, although typically only very large sources like volcanoes and major industrial activities like smelters will produce an appreciable signal in the satellite data. This means that in general, satellite SO2 data cannot be used directly for most air quality and health applications, but in certain specific regions, these SO2 sources can have major local impacts, and so it still may be relevant where source-specific SO2 emissions are of particular concern. One thing to note for sulfur dioxide retrievals is that certain assumptions must be made about where in the atmosphere the sulfur dioxide plumes are concentrated. Typically for air quality applications and in the absence of major volcanic activity, we recommend using products which assume near-surface emissions, such as the OMSO2E product from OMI, or the estimate using a polluted boundary layer assumption, which is part of the TROPOMI SO2 data product here. It's important to note that near surface here refers to the assumption about where the SO2 is concentrated, and that the data is still providing information on the concentration of SO2 for the full vertical column of the atmosphere. Finally, OMI's wider spectral range allows it to provide information on atmospheric carbon monoxide and methane. Carbon monoxide, with its relatively long atmospheric lifetime, is useful as a tracer for the long-range transport of pollutants, such as wildfire emissions. Methane is a potent greenhouse gas, and although it's not typically regulated as an air pollutant, it can still be important to look at, including as an indication of potential leaks from certain industrial activities like natural gas facilities, as well as more distributed emissions from activities like agriculture or landfills. Again, as Dr. Susan Annenberg discussed last week, and similar to the case for particulate matter, there exist various level 4 data products which combine satellite information with model outputs and surface level monitored data to estimate the surface level concentrations of the various trace gases from the different data sets. Spatial and temporal resolutions of these products vary according to the input data and the methodologies used, but very high resolution data sets can be derived by making assumptions about, for example, the local impacts which highway emissions could have. Again, these local level 4 data sets are most useful in cases where spatially and temporally complete data are needed for retrospective quantitative analysis. For more qualitative or exploratory analysis, or where more near real-time data are important, the level 3 or level 2 column concentration data from the satellites may be sufficient. Again, the NASA CDEC provides many of these relevant data sets. Before wrapping up our discussion of trace gases, I wanted to mention TEMPO. As Dr. Susan Annenberg mentioned in her presentation last week, this is a recently launched geostationary satellite mission, and in particular, it's a geostationary hyperspectral mission, which will provide hourly trace gas products over North America after it completes its checking out activities early next year. You can see an example of what these data will look like in the animation here. This will be a new capability for North America, and TEMPO will join a constellation of similar satellites, including the GEMS instrument launched recently for East Asia, and the Sentinel-4 satellite, which will cover Europe and North Africa in the future. In addition to providing higher temporal resolution for NO2 and other pollutants, a new approach will also create near-surface ozone data products, which will hopefully be able to overcome some of the limitations on near-surface ozone observation from space, which I discussed earlier. All of this will provide us with an exciting new data set to look at the hour-to-hour variations in trace gases across North America and set the stage for future missions like GeoXO to continue these measurements in the future. Again, I encourage you to visit the TEMPO website linked at the bottom of the slide to learn more and to join the TEMPO Early Adopters program, where you can practice analyzing TEMPO data currently available using their synthetic data sets. So, having learned about some specific satellite instruments and missions, I want to ask, if I want to track trends in particulate matter air pollution from 2000 to 2020 and compare state-level averages to assess the impacts of different state-level policies, which of the following instruments would be my best resource for getting the kind of data I need? MODIS, VIIRS, OMI, or TROPOMI? I'll wait a few seconds to let you pick your answer. So my choice here would be the MODIS instrument, and that's mainly driven by the time series I'm looking at. If I want data that goes all the way back to 2000, only MODIS was in operation back then. VIIRS launched much more recently. OMI launched back in 2004, but this is a hyperspectral instrument which is better suited to gas observations than the aerosol observations, which are related to my topic of concern for this study. So in this case, I would pick MODIS as my answer. To close out on this part of the training, I'd like to give a quick look at a few online NASA resources for accessing and visualizing satellite remote sensing data. First resource is NASA Worldview. If you haven't worked with satellite data before, I would recommend starting with Worldview. This is an online interactive browser which allows you to easily display many different satellite remote sensing data products. Its main focus is to provide quick access to near real-time satellite data. Some data sets are updated in Worldview within 3 hours of the observation being made. When you open up NASA Worldview, this is what the interface looks like. You'll see to start off with, there's this Welcome to Worldview with some examples of different satellite data sets you can use and look at in Worldview. If you're new to Worldview, I'd encourage you to take a look at some of these examples. I'm going to close out of this right now and just show you what the interface looks like. So you can see in the background here, there's an image of the Earth with some coastline showing up, as you can see here. And the color imagery is from the true color imagery from the Terra MODIS instrument, which is you can see here. I can use these buttons here to toggle different layers. So for example, I can turn on the SWOMI NPP VIIRS instrument, and that's what that looks like here. Or the NOAA 20 VIIRS instrument, and that's what that looks like here. So that's these layers on the left-hand slide. I'll go back to those a little bit later. On the bottom, this is the time slider which I can use to scroll backwards and forwards in time. You can see as I scroll back in time, different satellite data is being populated there. I can also use these date selector here to select the date of interest. And then I can pan and zoom using either my mouse controls, clicking and dragging to pan, and using my mouse wheel to zoom. Or on this side of the screen, there's buttons related to zooming in and out. Also in the upper corner of the screen here, there's information on the tool, which you can click on there if you want more information. And if you, in particular, if you click this Explore Worldview button, this brings up the introduction again. So just to show you how I might use this tool, I'm going to scroll back to a major air quality event that happened in my area, the northeastern US, on about June 6th. which was when the northeastern part of the United States here was impacted by wildfire smoke from Canada. And you can see in the true color imagery, which is shown here, you can even see this impact right there. So you have the wildfires taking place here, the smoke coming off of those, more wildfires here with the smoke coming out, and you can see the very dense smoke clouds over New York there and the northeastern United States more generally. If we want to look at some of the data products I've discussed today, we would use this Add Layers button to add new layers. So if I click on this, it brings up a menu which categorizes different types of satellite data sets into these different application areas. And you can see air quality is front and center here, which is really nice. Let's look at the aerosol optical depth. So if I pull down this aerosol optical depth menu, you'll see some of the instruments we talked today, the MODIS instrument, the VIIRS instrument. I want to go to, let's see, maybe Aqua and Terra MODIS combined aerosol optical depth product. So this is one of the data products available. You'll see if you scroll for Aqua particularly, you'll see deep blue algorithm, the dark target algorithm I mentioned. We'll just stick with this combined just to illustrate what this looks like. Let me close out of that. So you can see what this data product looks like here. You can see the aerosol optical depth scale here, and I'm just going to use these options to pick a different color scale just to illustrate what that looks like. So you can see this imagery here, the areas of high aerosol optical depth where there's very dense smoke, and you can even see the interference that the smoke, the densest parts of the smoke, are causing with these retrieval algorithms, where we're not even able to retrieve aerosol optical depth in some of these very dense smoke areas. You can also see that clouds are having a similar effect in a lot of areas, blocking the aerosol optical depth information. But even so, we're picking up on some areas of very high aerosol optical depth. Just to illustrate another example of this, I'll bring up another area. I can also bring up, using this menu, the fires and thermal anomalies here, and I'll pick the Aqua and Terra MODIS fire and thermal anomalies product. I'll check that, close out, and you can see these orange dots which have shown up indicating the locations of fires detected by the satellite. So you can really see how you can use this tool to overlay a lot of different data sets and just get a broad look at what the data is telling us in terms of information about air quality, fires, and various other things that we might want to look at. Another website I want to point out is Earth Data Search. While Worldview was more focused on the visualization of data, Earth Data Search focuses on selecting and downloading data to conduct your own quantitative analysis. It provides options to filter data according to the instrument, the observation type, the data product, as well as to subset data using temporal and geographic search filters. Once selected, it provides details about how to access and download the selected data. So this is what the Earth Data Search tool looks like. You can see it's a little bit similar to the Worldview tool. We have a map of the world in the background here, some options on the left for the different layers we can look at. Before we get started, I want to encourage you to take a look at the upper right-hand corner here and check if you're logged in. In this case, I'm not logged in. To use Earth Data Search in the most effective way, you need to log in with your Earth Data account. These are free accounts to create. I've already created one, so it's logging me in automatically here. If you don't have an account, again, it's free to create, and there will be some instructions on how to create that account and log in with it. And that's a useful account across many different NASA online services. So you can see here that it has my name. I'm logged into the account. So what Earth Data Search, as I mentioned, is most useful for is for finding and selecting different data sets of interest. And you can do that in a couple of different ways. There are many different filter options on the left-hand side here. You can search by different keywords. For example, atmosphere, I would go in there to look for air quality information, for example. You can search by platforms and instruments. For example, if I go into instrument and I scroll down, I'll eventually find MODIS, OMI on this list. MODIS is on that list too. You can search by processing levels I mentioned, from level 0 to level 4, and some additional specialized processing levels for different products are also available there. You can search in terms of the resolution, the data latency. So you can use those keywords to filter down things. I also find it's very easy if you happen to know the code of a satellite data product, you can search for it just using the search bar up here. So I happen to know that for the Tropomi dataset, which I'm going to be demonstrating here. So the dataset I care about starts out in this way. So if I type that in and click the search button, give it a couple seconds to search, and it comes up with the Tropomi datasets I'm interested in. This is the level 2 nitrogen dioxide dataset. This is the most recent high resolution dataset. You can see some information, basic information about the dataset here. If you click on this I button, this brings up more detailed information about this data set, and there would even be a link to the landing page, the dataset landing page for that particular data set. I'm going to press the little plus button here, and that adds this data set to my search collection. You can see here it says 27,000 granules. A granule is basically a term for basically a file's worth of satellite data. So when the satellite's orbiting, it's collecting data continuously or nearly continuously. And to organize all that data, we typically divide it into granules, which are basically amount to files containing some subset of the satellite data. For Tropomi, the way they divide the granules is every orbit, or really every half orbit on the sunlit side of the Earth, gets its own granule. So you can see here there's 27,000 data granules, which is a lot more information than I need. So I want to filter that down a little bit more. And I'm going to do that in terms of spatial and temporal search filters. So spatially, I want to focus in on the area where I'm situated, which is near the NASA Goddard Space Flight Center near DC. The way I apply these spatial search filters is with this button up in the upper left here. If I click on that, I have a couple of options to use, draw a rectangle or create a point or circle, or even use a shape file to designate my spatial area of interest. I want to just do with a simple point. So if I click on the point there, I can just drop it on the map approximately where Goddard Space Flight Center is. And that'll apply a spatial filter to my search criteria. And you can see it's come up here now where there's now only 2,559 granules are covering this particular location. I also want to do temporal filtering, which I'll do with this filter button here. And I can pick a start and end time of interest. And I'm going to go to the beginning of June 2023, which is the time of that high wildfire pollution event in the northeastern United States, which I showed in the worldview example. And I'm going to go from the beginning of the month to the middle of the month just to cover that period. So if I click this apply button, it'll again apply that temporal filter to my search criteria. And now we have a much more reasonable 20 data granules selected. So when I'm satisfied that I've applied the filters and I've picked the data sets I'm interested in, the next step would be to go in the upper right corner here to the My Project button, and you click on that. This will bring up basically a summary of the data which you've collected. So on the bottom, you have the time series. This green bar is showing when that Tropomi data is available, and this red interval is showing that the time period I selected. In the map, you again see sort of the spatial location I selected showing up there, and then a summary here of what I've actually selected. So it's the level 2 NO2 data product from Tropomi, and 20 data granules match my search, and you can see it's about 11 gigabytes of total information there. And I can go down this list here to look at how I'd like to access and download my data. Usually the direct download option is the best, but there's some customizable options that you can pick there. And when you're ready, you click on the download data button here. And that will bring you to a new screen, which will provide information about how to access your data. And it gives you a couple of different options about how you might want to do this. You can download the files one by one directly here. These are all links to the individual granule files. So you can just click on those to download them directly. In this download script option here, there's a script which can be run in the C programming languages. There's some instructions here about how to run that script, and that'll go and automatically go through the list of files, which you can see here, and download them to your computer. And then finally, if you're working in the cloud with Amazon Web Services, there's in the AWS S3 Access tab, there's information and some instructions and documentation on how to access those data on the cloud through Amazon Web Services. So many data sets from NASA are in the process of or have already been migrated to what's called the Earth Data Cloud, which is method whereby you'd be able to access a lot of these data products indirectly on the cloud itself. While Earth Data Search allows you to download satellite data to do your own analysis, the objective of NASA Giovanni is to allow certain common types of data analysis to be performed online without you having to download the data and set up the analysis yourself. NASA Giovanni operates with the level 3 and level 4 data products, which you'll remember are the gridded satellite data and the gridded combinations of satellite model and other data sources. This is an important requirement for using Giovanni and a limitation. Some information is only available through level 2 data products, and if you're looking to do very high spatial resolution analysis, the level 3 and 4 data products may be too coarse. Nevertheless, Giovanni is a useful tool to quickly perform simple analyses and plot results without needing any coding knowledge. So this is what the NASA Giovanni tool looks like. You can see the interface is a little bit similar to the other ones we've seen before. We have some search criteria and filters on the left-hand side of the screen, temporal, date range, and region selection options at the top. The upper right-hand corner, again, you can see that I'm logged in as myself to my Earth Data account. This is the same Earth Data account you used with the Earth Data Search website earlier. Again, you need to log into your Earth Data account there to be able to use the full functionality of NASA Giovanni. Otherwise, there are some limitations on the functionality. But again, the account is free. So if you want to do that, I'd encourage you to definitely sign up for an Earth Data account. So in this example, I'm going to look at some data from the OMI satellite. So again, I can kind of use a keyword search to pick my data set of interest. I'm going to just show how these filters work. So for example, I'm interested in OMI NO2 data. I can look in the measurement column here, scroll down, you'll see a lot of different options. One of them is NO2. And if I check that, we'll give it a second to search through the options. And you can see here, 2 of the OMI data products have shown up, the total column and the tropospheric column NO2. I'm going to select the tropospheric column NO2. You can see here some information about the data set, the units, the source, the temporal and spatial resolution. Again, this is a gridded data product, so it's on a fixed latitude, longitude grid spatial resolution. And then finally, in the upper left corner here, this is the real kind of core of Giovanni, which is providing different sorts of analysis options. And you can see the available analysis options listed here. And these are some sort of typical simple activities you might want to do with data sets. For example, create a time average map. So create a map of just the data over a specific location and time range. There are also maps where you can take an average difference map. For example, if I selected 2 data sets, I can look at the differences between those data sets, average them, and map those differences. Similarly, a correlation map, if I select 2 data sets, I can map the correlation between the data sets. Scatter plots, also comparing different data sets. I can look at time series plots. So for either individual locations or area averages, in this case, it's an area average difference, I can plot the time series for the average for that area. I could plot, again, recurring time series. Also, there's a recurring averages option, which I'll show a bit later. So if you wanted to look at, for example, the recurring patterns at daily or weekly, monthly, seasonal frequencies, you can use these recurring average options to do that. And there's some other options related to vertical profiles if you're interested more in the vertical profiles of the atmosphere. So just to illustrate this tool, I'm going to start off with a simple time average map option. And I'm going to, again, go back to that wildfire event that happened in early June of this year. So I'm going to go from 2023, June 1st, to maybe June 10th. That's my date range of interest. And then I would select the spatial area of interest. I can type in the coordinates of the bounding box. I can also click on this button to bring up a little map and maybe zoom in on North America and draw a little bounding box over, the United States, maybe get a little bit more of Canada in there too. And that's my area of interest for this analysis. I can also refine that if I'm not satisfied. Once I pick the data set and the plot I want to create and the time and region of interest, I go down and I hit the plot data option here. This may take a few seconds or even a few minutes if you're launching a more complicated analysis to run. Hopefully it won't take too long to run now. But once that analysis is done, you can see it's generated a map of the surface level NO2 over this area. I can use the options of the map up here to choose different overlays. If I click on the options here, I have different options for the color palette. So let's pick maybe a blue type of a color palette like this one and add that, and I can click the replot button there and it'll generate a plot with the different color palettes. You can choose the data ranges of interest to you there as well. So looking at this map, you can see, we've averaged about 10 days worth of data, and you are actually seeing some NO2 spikes up in Canada here where we saw those fires in the true color imagery from WorldView. Note that, as I mentioned earlier, NO2 tends to be concentrated a lot more in the immediate vicinity of the emission sources, so it kind of makes sense that the NO2 is more concentrated where the fires are rather than spreading out over the whole northeastern Canada and the United States, as we saw in the MODIS, the aerosol optical depth information. But again, you can kind of see the averages here, and this gives you a sense of what you can get with an average map view. Let's go back right now to the data selection and look at the data in a little bit of a different way. So let's, instead of a time average map, let's look at a recurring average time series. And what I'm going to do here is I'm going to pick the same days of my analysis, so June 1st to, let's say, June 10th. And I'm going to look at the recurring concentrations, average concentrations of NO2 between those dates from the years 2004, which is when the OMI instrument started operating, to 2023, which is when the most recent data is available. And for this analysis, I'm actually going to zoom in a little bit closer to, I have to click this little button here to bring up a panning option, and then click this to make a square. I'm going to zoom in a little bit closer on like just the northeastern US that was most heavily impacted by this event and see what that looks like. So I'm now going to hit the plot data button again. And again, this will take a couple seconds or even a couple minutes to perform the analysis I told it to do. So once the analysis is done, you can see that it's generated this time series plot from the data. You can see by looking at this how the NO2 has really varied over this region. You can actually see in 2023 it was some of the lowest concentrations of NO2 in this region and for this particular time interval. So the NO2 from this particular wildfire event, the NO2 was not really a major impact on the local concentrations, probably. There are, of course, some nuances to this analysis. For example, we know that cloud cover and dense smoke cover can block some satellite instrument observations. So it may just be that there was some higher surface level NO2 concentrations, but the dense smoke in the atmosphere prevented the satellite from seeing that. We'd have to dig a little bit more into the data to see whether or not that is the case. But this analysis really gives us a good overview of the trends in air quality. So you can kind of see, the general trend, as we've been seeing for many places in the United States, is reduced NO2 concentrations and improving air quality over time. You can see in 2020 there was a slight dip in air quality. If we picked a different area of coverage and a different time range, we might see a little bit bigger of a dip there. And that's typically associated with the COVID lockdown. So when those lockdowns happened, we saw less traffic on the streets, and traffic is a major source of NO2. So that showed up more or less clearly in different satellite data sets for different areas and for different specific time periods. I picked a June 1st to June 10th. That's a pretty short time interval. So it may not, and I picked a region that covered a large portion of the country, including more rural areas. So that signal of reduced NO2 due to those lockdowns is not as strong in this particular analysis than it might be in an analysis that focused a little bit more on an urban area and looked at a longer period of time to really get the longer term trends in that. But again, hopefully this has shown you just an illustrative example of how you can use Giovanni to do these kinds of analyses And without having to download the data yourself, you can get some insights into what might be happening quantitatively in the satellite data. So to summarize today's training, satellite remote sensing data can be used to complement surface-based air quality monitors to fill gaps in our understanding of air quality around the world. Satellites usually provide retrievals of column quantities like aerosol optical depth. It's important to remember that these aren't the same as surface level quantities like PM2.5 concentrations, and they can't be directly quantitatively compared, but they can provide indicative qualitative information and can be used together with other information from models and surface monitors to create level 4 data products relevant for surface level air quality. When using satellite data for different applications, it's important to remember that different instruments and different products with different processing levels can have different spatial and temporal resolutions. For environmental justice applications, it's important to match these spatial and temporal scales to the scale of your analysis. For example, if you are looking at spatial disparities in a potential pollutant exposure, the spatial resolution of the satellite data product you're using should be similar to or finer than the spatial scale of the disparities you're considering. Also, wherever feasible, you should try to verify the ability of the satellite data product to identify disparities in near-surface pollutant concentrations at the relevant spatial and temporal scales by performing comparisons from satellite data to surface-based data in or near your study domain. Finally, NASA provides some free online resources for visualizing, accessing, and analyzing satellite data products, which I walked through briefly today. Looking ahead to our next and final training session of this series at the same day and time next week, we'll be looking at some interactive exercises demonstrating how to combine satellite data and demographic data for analysis using the EJ Screen tool, as well as Python data analysis code. Between this session and the next, if you'd like to get familiarized with some of the data products I've discussed today, I would encourage you to take a look at the Worldview or Giovanni web tools I demonstrated. You can zoom into your local community or an area that's of interest to you and think back to a significant air quality event in your area, or try to pick a representative day or time interval and take a look at the various satellite data sets for aerosols and trace gases and what they look like at this location and time. If you see anything of interest or which you didn't expect to see in the satellite data, or if you don't see something which you think you should have, make a note of it. If you registered for the HeyCast forum after part 1, consider posting a screenshot of what you find there for us to discuss. Just as a reminder, this is a purely optional exercise and is not a part of the homework which will be sent out at the end of the training course. This is just a suggestion if you'd like to start exploring some of the data on your own. A homework assignment, which will be posted at the end of the training course, will be available on the training webpage on the day of the final training part. That's September 6th, and it will be due 2 weeks later, September 20th. To get a certificate for completion of this course, you'll need to attend all 3 webinars live and complete the homework assignment before the given deadline. If you do that, you'll receive a certificate via email about 2 weeks later. Here's my contact information and links to the RSET webpage, as well as other NASA capacity building program web pages. And finally, here are some resources and links to many of the materials, websites, and datasets which I mentioned today, which can provide some further guidance as to how to best access and use these satellite datasets for different types of analysis. Thank you very much for your attention during today's training. We'll now move into the question and answer portion of the training.
And I realize I misspoke on the slide a couple minutes ago. The training certificates will be sent out about 2 months after the training, not 2 weeks. The information in the slide was correct. So now we can move on to the question and answers. Question 1, would stricter air quality standards, the NAAQS in the US, administered by the EPA, show more widespread cases of underserved communities across the United States? And how would that have more profound effect on government action to resolve these cases of EJ? I would say that in terms of studying environmental justice issues, as we've been discussing in these trainings, the exact air quality standards are not as relevant as the disparities in exposure between different population groups. We learned a little bit more about that in part 1, and in part 3, we'll be actually giving some examples of how to assess and quantify that using some data analysis examples. But in terms of for example, just studying environmental justice, the exact air quality standards are, as I said, less relevant than the differences in exposure of different population groups. However, for the second part, in terms of government action to resolve cases of environmental justice, that is where the air quality standards would play a role. For question 2, which satellites are in polar orbit? I went over this during the training. I mentioned several satellites. Of course, I'm not going through every satellite that's in a polar orbit. I just focused on the satellites that were most relevant for air quality applications. So of the satellites I mentioned, these include the Aqua and Terra satellites, which have the MODIS instrument, the Aura satellite, which has the OMI instrument, and the SNPP NOAA 20 and NOAA 21 satellites, which have the VIIRS instrument. Those are the sort of multispectral instruments, the VIIRS and the MODIS. And for hyperspectral instruments is OMI and the TROPOMI instrument, which is on the Sentinel-5 precursor or S5P satellite. So those were the main satellites I discussed during the training, which are in the polar orbit. For question 3, does NASA have any open source models that can be loaded into Python for real-time analysis? I'm not sure exactly what this is referring to in terms of models. I will say in terms of atmospheric chemistry models, I'm not aware of any that can be run for real-time analysis in Python. These are very complex model systems that have a lot of inputs and a lot of variables and require a lot of processing power to run. For example, the Global Modeling and Assimilation Office, which is where I work at NASA, runs several models in what's called the GEOS family, the Goddard Earth Observing System family of models. And while these models are openly available, you can go to GitHub and download the source code. They require quite a bit of expertise and quite a bit of computational resources to be effectively set up and run. If you were referring to like machine learning models or data analysis type models, there are Python examples we have. For example, in part 3 of this training, we'll be giving some Python code out, which is an example of how to analyze demographic and NO2 concentration data together to look at environmental justice issues. So we'll be giving that demonstration in Python. It's not a real-time analysis. It'll be looking at some retrospective data, but it will be an example. And if you're interested in machine learning, RSET recently had a training on the fundamentals of machine learning for Earth Science course. So that that gave several examples of how different machine learning models, including open source models in Python, can be used to answer many types of Earth science questions, including questions related to air quality and potentially questions related to environmental justice. So question 4, could you please explain the hyperspectral and multispectral differences again in equations? I think the exact equations that describe retrievals from hyperspectral and multispectral instruments are kind of beyond the scope of this course, and frankly something that I'm not an expert in. You have to speak to the sort of designers of these instruments and the algorithms, which is not something I'm directly involved with. But and if you wanted to learn more about those equations, I'd recommend searching out textbooks or university courses, if you have access to them, that go through the fundamentals of optics and concepts of remote sensing. And they'll typically go through the fundamental optical and physics properties that govern remote sensing and then how those are applied. At a more conceptual level, which is where this training is more focused, you can think of the differences between multispectral and hyperspectral instruments as a hyperspectral instrument, by providing more information about the intensities of light at different frequencies, gives you more degrees of freedom in terms of designing algorithms that can identify slight differences in data caused by different effects. So as a kind of analogy for this, if you were thinking about the presence of a gas causing changes in the spectrum of light, if you think of that as a fingerprint, and we're trying to identify different gases by is sort of analogous to distinguishing different fingerprints from each other. So if you want to do that, the better and sharper picture you had of those fingerprints would give you an easier job of distinguishing fingerprints from each other. Whereas if you were using a blurry picture of a fingerprint, it would be much harder to tell whose finger that fingerprint belongs to. So that's kind of just a conceptual analogy of what we're trying to do and why a hyperspectral resolution, which in this analogy is the sharper image of the fingerprint, is more useful for telling different trace gases apart from each other than a blurrier image in this analogy, which corresponds to a multispectral instrument. And again, the fundamentals of remote sensing course goes into this in a little bit more detail, not in terms of the equations, but in terms of more of the conceptual ideas behind these concepts. All right, so for question 5, what would be a good resource to learn about row anomalies and changes in older satellites? So for the row anomaly specifically, that's something that's affecting the OMI instrument. You can go to the OMI webpage. The OMI instrument operators have a webpage dedicated to the instrument, and they keep that up to date with information about how the instrument's performing, including any kind of degradation in the sensor. We also have a training, an RSET training on, the training is referring to the TROPOMI instrument, but part 1 of that training does cover the OMI instrument and covers, among other things, the row anomaly and how that's affecting the OMI data. So if you're interested in that. More generally about changes in older satellites, again, the web pages for these satellites will typically publish summaries or reports on the data quality of the instrument data that these satellites are producing. I know the TROPOMI webpage has a whole section of its website dedicated to different reports, which are periodically generated about the quality of the satellite data and how well it agrees with other information sources that are measuring similar things. And the instrument teams which are operating these satellites also routinely publish scientific papers where they summarize these results. So, if you're interested in specifics about a specific satellite, I'd advise going to the satellite's website and looking there to see what the latest reports are about the data quality. For question 6, what would be a good resource to learn about the impact of smoke on satellite data? For example, what extent of smoke blocks the instrument? We had a recent training on both the MODIS and the VIIRS instruments, which are, again, aerosol instruments, and we went into a little bit of detail on that about the limitations of those instruments. We also had a recent NASA RSET training on wildfires, and in part 3 of that training, we also addressed this question on the smoke impacts on satellite data. In this case, it was specifically referring to the ability of the satellites to detect active fires, which is what the focus of that training was. So if that's of interest to you, you can check that out. I would say that in general, the areas of thick cloud cover or thick smoke cover will cause larger uncertainties in the satellite data and eventually prevent a reliable retrieval. And when this happens, this is usually indicated by a corresponding data quality flag in the level 2 data product. So there will be in the level 2 data products especially, every pixel or every value usually has an associated quality flag, which will it differs slightly depending on exactly the instrument and the retrieval that's being used, but they will generally give information on the quality of the retrieval, including whether there was heavy cloud or heavy smoke cover that potentially or actually caused a problem with the retrieval algorithm. And as I mentioned earlier, in the level 3 data products, if you look into the documentation of those products, there's usually some description of quality criteria that were used to create those products. So, areas of thick clouds or thick smoke might have been, identified using those quality flags and removed from the data set before the level 3 data product was created. And that would be detailed in the documentation for those data products. So that would be my recommendations to look for more information about that. Question 7, will Maya be able to provide vertical or 3D air column information? So we actually had I had a presentation, I listened to a presentation recently by someone on the Maya mission, and their information to me, again, this is secondhand, but there will be some vertical profile information about aerosols from the Maya mission, but it's not a main focus of the mission. Again, you can go to the Maya webpage for more details about this, but it's not a primary focus, so they're not really going to be, even if they do provide some vertical profile information, it won't be a primary focus of the mission. If you are interested in vertical profiles of aerosols, which many people are, especially if you're sort of an atmospheric chemist, that's very important information. I'd refer you to the Calypso mission, which is a mission which uses a LiDAR, a laser that beams down from space, and it reflects off of various things, including clouds and aerosols in the atmosphere, and gives information on the vertical profile or the 3D air column information on the vertical distribution of those aerosols. Unfortunately, that's ended recently, but of course, if you were looking at historical data, you can still get access to that data. Question 8, will any new or upcoming missions provide good methane emission info that could help identify leaks and releases? I think the main resource I'd direct you to for this is the EMIT mission from NASA, and they have a web page which is linked here. And again, we'll be sending out these Q&A documents in a few days, so you'll have access to them on the training web page to get all these links. But anyway, the EMIT mission is one of NASA's main missions, which is looking at methane. I also mentioned briefly, the TRPOMI satellite also has a methane data product. It's not because the resolution's a little bit lower there. It's more for looking at sort of regional factors. So unless it's a very large leak or emission, it probably wouldn't register in the TRPOMI data set unless it covers a very wide area. So for I think what you're getting at here with leaks and releases from industrial sources or pipeline leaks, the EMIT mission would probably be your best resource for that. Question 9, are all these sensors passive sensors? There is no nighttime data collection yet. So yes, that's true. For this training, we focused on the passive instruments. They are the most typically used for air quality applications. There are active instruments as well. The Calypso mission, which I mentioned earlier, is an active mission. It uses a LiDAR. The general limitation of these active missions is that they typically have a very narrow swath width, which means that they only cover a very small portion of the Earth's surface on each orbit, or conversely, it would take many orbits and a long period of time to cover the full surface of the Earth with data. So they're not typically as useful for near real-time applications and air quality applications as the OMEs and the TRPOMEs, which are passive instruments, but they do exist and they are of course useful. In terms of nighttime data collection, again, yeah, because these are passive instruments that mostly rely on sunlight, generally there are no nighttime retrievals of the air quality relevant information like the trace gas columns or the aerosol optical depth. I will note that again, there has been some recent work in this area. I'll be hearing in a few weeks about some recent work that is very interesting on looking at using moonlight instead of sunlight, basically, to get aerosol optical depth information. Of course, there are a lot of limitations to that. You need only certain times of month where the moonlight is bright enough to get enough of a signal to get this kind of information, but still a very interesting concept and approach. But it's still in sort of a research phase. It's not yet at a point where we can do this operationally at any kind of a scale to get information. But so yes, in general, I would say probably no nighttime data collection for these air quality relevant information. If you're looking at, of course, a different concept like light at night, which we discussed in part 1 of the training, obviously that is a nighttime piece of information. It's measuring that light that's being emitted artificially at night from the Earth. So that's a different problem. but referring specifically to air quality, that's correct. There's no general nighttime data sets. Question 10, could MISR be useful for measuring particles, just like the MODIS? Yes, so MISR is another multi-angle imager. So it's useful more for getting information about the properties of atmospheric particles. So I mentioned the Maya mission, which is going to use multiple angle images to get information about the different properties of aerosols. MISR used a very similar concept where it had multiple cameras at different angles, and it gathered information as it passed overhead at multiple angles, and using that information, you can infer some properties of aerosols like the type, the size, and a little bit about the altitude, the vertical profiles. So I would say while it's similar to MODIS, it does have some limitations. It has a smaller swath width, so it doesn't provide the same sort of 1 to 2 day coverage as MODIS did. But the reason we're interested in it, basically we can combine the information from MISR together with the MODIS information to build an overall better understanding of aerosols than we would get with either instrument by itself. So that's what I would say about that. Question 11, can datasets be overlapped in Giovanni like you did in Worldview? So again, I only showed very limited examples of what you can do in Giovanni, and there are some plotting options that do allow you to select multiple datasets and compare them with each other. For example, there's a difference plot. You can select 2 datasets and then plot the difference between those 2 datasets. There's also a correlation plot. You can, if you have sort of 2 time series datasets, you can select both datasets and then plot the correlation between those 2 datasets. But it's not quite the same thing as I think what you're asking about, which is overlaying one on top of the other. So yeah, in general, in Giovanni, you wouldn't be able to overlay data sets on top of one another like was seen in Worldview, but there are some plotting options that allow you to compare 2 data sets to each other. Question 12, when will the new North America satellite data be available? I'm assuming here that you're referring to the Tempo mission that I talked about. So that was actually launched in April of this year, and they're anticipating the release of the full data products that they had planned to produce for this mission sometime early next year, if all goes well. I will note that just a few days ago, the team released some of its what they call first light imagery. Basically, they're in the early stages of checking out the instrument, making sure everything's working well, and testing out their algorithms. And as part of that test, they did produce some data. It's not like the full final data that they expect to produce, but it's some preliminary data, and it's very interesting. So I put a link in the Q&A document here, which again you'll have access to in a few days when we're finished going through and finalizing our answers, and you'll be able to look at some of that imagery. Question 13, how to improve air pollution retrieval techniques by artificial intelligence and machine learning algorithms? Any case study? So I alluded to this earlier, but most of the aerosol retrievals, the satellite retrieval algorithms, make use of the basic radiative transfer theory, the optical theory, and go from that theory to the practical algorithms that are used to make these retrievals. There has been research in using machine learning for this problem, either fully replacing the radiative transfer models with some kind of machine learning model, or more commonly what's done is specific parts of that radiative transfer equation that are particularly computationally intensive might be simplified using a machine learning algorithm, a proxy model, anyway, a machine learning algorithm that replaces sort of the more computationally burdensome parts of the process and perform reasonably well. Yeah, so we'll have to follow up and look for some specific examples of that to refer you to. But yes, that is something that is being researched. Question 14, satellite measurement generates some uncertainty, especially in areas of complex orography. This leads to few valid satellite measurements or significant quality control. How could it be handled, or what would you suggest to handle data in a PM2.5 particle material investigation using 550 nanometer AOD? So yeah, that's definitely true. Clouds and other sources of uncertainty definitely interfere with the satellite data retrievals. And then depending on your area of interest, particularly if it's a very small area, you may need to average data together spatially or temporally to collect enough data to sort of overcome via averaging the uncertainties and get a more robust result. So yeah, unfortunately, there's not really a sort of a general answer for that, but you're very correct in identifying the fact that these factors all lead to uncertainty in the measurements. And yeah, I'll just say the general solution is sort of collecting more data and using that to kind of overwhelm or average out the uncertainties until you get a sufficiently robust end result. Question 15, CDAC has PM2.5 daily and annual at 1 kilometer resolution, but this set ends at 2016. Is there a time frame for updates to that set, or any suggestions on algorithms available to update these models with available data? Yeah, so that's a very good question. There is not through CDAC, but through the Washington University Atmospheric Composition Group, which the link's in the answer here. They do have a little bit more recent information, I think available up through 2021. But sort of as I mentioned, for these level 4 data products, there is a lot of data processing that goes into creating these data sets. And so can be quite a bit of sort of delay behind near real time for some of these data sets. So you're not always going to have access to these kind of data fusion products or the level 4 data products. There's going to be quite a bit of lag time associated with those. So yeah, we don't have a specific time frame, I think, for those updates. We'll see if we can reach out to someone and get more information. But in general, we try to keep them up to date, but there will be some delays. Question 16. I love this part of the training. In the beginning, you had discussed the on-ground monitors and discrepancies between the governmental approved and calibrated monitors and the cheap monitors. How could the AOD analysis show which monitors are more accurate? So that's a very good question. And thank you for that you love this part of the training. So yeah, that's a very interesting question. I would say that, yeah, it's sort of a weight of evidence approach that you would take here. So you're thinking about 3 different sources of information. You have your regulatory monitors, which are typically highly accurate, but there's not that many of them. You have the low-cost sensors, which there's more of them, but the data quality of any individual sensor is typically less than a government monitor would be. And then you have the aerosol optical depth, which is the greatest in terms of the spatial coverage of this domain, probably, unless there's a lot of clouds or something like that. But it is still a column quantity, so it's not necessarily related to what's happening at the surface level. So my general advice would be to sort of intercompare all these data sources. And if you can show, let's say, okay, there's a good agreement maybe between your government regulatory monitors and AOD, and if that is established, then you can sort of trust that the AOD is maybe giving you a good sense of what the variability is. And then if you compared that with your the cheaper monitors, the low-cost sensors, if you were seeing the same kind of agreement between the low-cost sensors and the aerosol optical depth, that kind of gives you more confidence that, let's say, all your data sources are agreeing in terms of what the general trends are, what the general patterns are. And through that agreement, you have sort of higher confidence in each of the individual data sources, and then you might be able to go and say something about that. So that's, that's a bit high level and a bit vague, but that's my general guidance there. And I'd say, yeah, this is definitely an area of active research in how we can combine the satellite, the ground-based monitors, low-cost sensors, all our data sources together in the best way, and get the best use out of each of these data sources while still respecting the fact that they each have their own limitations. Question 17. Does NASA have any datasets available as OGC map services or other types of REST services that could be easily and directly loaded into web map tools like ArcGIS Pro without having to download and process the data first? All right, so that's a good question, and I'm not sure I know the answer to it. There is, I'm unfortunately blanking on the name right now, but I'll go back and look it up and put it in these responses. There is an effort to create a little bit more of a sort of web-friendly versions of some of these data sets, which can be more easily ported into things like ArcGIS. There's also some efforts where we're trying to get various NASA data sets uploaded into tools like Google Earth Engine, and various NASA data sets already exist in Google Earth Engine, but making that more available. And then in terms of APIs, there are, I mentioned very briefly earlier on, but just to talk about it a little bit more, there's an effort to migrate a lot of our data sets into what we're calling the Earth Data Cloud, which is sort of moving them from sort of disk storage to more cloud-based storage. And as part of that, we are developing also APIs to assist with things like querying the data. So I showed you an example of walking through a process using Earth Data Search, where I picked a data set and then I subsetted it by space and by time and got a list of granules, satellite granules associated with that. There is an API that basically does that process, the Earth Data Search API. So you can use the API to basically automate that kind of a process where you can feed it a time range or a location areas of interest, and it will return the data granules of interest, and then you go in and you set up a different section of code which goes and automatically accesses or downloads that granule. So yeah, we are sort of moving towards making things a little bit more interoperable in those ways. Again, I don't know specifically about OGC maps, so we'll have to look into that in more detail and get back to you. Question 18, how can I convert the OMI tropospheric NO2 units in molecules per square centimeter for PPV to compare with NO2 surface measured data? So as we mentioned during the training, the satellite, the OMI satellite in this case, is measuring a column quantity. In this case, the tropospheric NO2, so the amount of NO2 in the tropospheric portion of the atmosphere, which is the lower portion of the atmosphere. And that's refers to the full column there, versus the parts per billion, which is a volumetric measurement, which in this case, I'm assuming you're referring to the specific, I guess, yeah, you said sort of the surface measurement. So this is a parts per billion volume at the surface level specifically. So converting between those two is not necessarily straightforward. In general, it requires what I mentioned earlier, which is the level 4 data products, where we take the satellite information and then we use other additional information. One approach is to use a model, a global atmospheric model. The model will produce its own estimates of what the column, the tropospheric column concentration is, and that can be compared directly to what the satellite's seeing in terms of its column concentration. The model also produces an estimate of what the surface level concentration is in parts per billion. And by taking that model and maybe assuming that the model's correct in terms of getting the ratio correct, but it may not have gotten the value correct, and then use that ratio multiplied by the measurement from the satellite, which we assume is more correct because it's an actual measurement instead of a model, and then use that ratio, and you can convert in that fashion. So you basically need to bring in an external source of information, whether that's a model that tells you what the relationship between these two quantities is at a given location and time, whether it's surface data, so you take the satellite image and if you have a surface-based measurement within that satellite image swath taken at the same time the satellite was passing overhead, and if you have enough of those, you can build up enough of a data set where you get a robust regression between the two. You can use that regression to convert from the column to the surface quantities. or you can use some combination of these methods and multiple data sources. And that's typically what these level 4 data products that I was referring to earlier do. They use multiple different sources of information, and they kind of converge on the best estimate of the surface level NO2 from all these sources. So I would say that's the general solution. It's not something, unfortunately, that we have a specific algorithm that you can apply that works always everywhere. It's very much something that needs to be sort of worked on, and there are various approaches that can be done, and that's why we have these level 4 data products that apply these different approaches, and we produce those level 4 data products from that. So question 19, how accurate is the air quality data collected from satellites, especially in areas with varying environmental conditions? What are the main sources of uncertainty in satellite-based air quality measurements, and how are they addressed? So yeah, that's sort of a general question about sort of the purpose of this part was to kind of provide some general answers to that. So again, there are several sources of uncertainty. There's sort of the inherent uncertainty in the satellite retrievals. So no instrument is perfect, and with any kind of measurement, there's a little bit of uncertainty in the retrieval itself. Then there's some additional uncertainty due to, for air quality specifically, converting between what the satellite is seeing, which is the full atmosphere, to what's most relevant for air quality, which is I discussed in the previous question, which is the surface level concentration. So you're needing additional data sources, like I mentioned, the models or the ground-based sensors, to make that conversion. There's also the fact that the satellites have limited coverage, either due to cloud cover or due to nighttime, or just simply due to the satellite not being overhead all the time in the case of a polar orbiting satellite. And so if you're trying to figure out, what's the average concentration throughout the day, the satellite's only passing over at a specific time of day, you need to make some assumptions about, what's happening at all the other times of day when the satellite's not overhead, or what's happening at night when the satellite's not collecting any information. So those are the sources of uncertainty. In terms of how they're addressed, again, kind of averaging over long periods of time to reduce some of the more random sources of uncertainty, especially in terms of data being blocked due to cloud cover. Just by going for a longer period of time, you have more cloud-free pixels available, and you'll get a more robust result that way. Of course, some sources of uncertainty wouldn't be reduced by that method. For example, if you're thinking about the nighttime concentrations and you only had satellite data during the daytime, no amount of averaging of that daytime data is going to tell you anything about what's happening at night. And that's where bringing in other information sources like models, like ground-based measurements, comes into play. Kind of as I alluded to in the previous answer, kind of using these multiple sources of information to try to home in on the best estimate of the quantity you're interested in. I think I'll leave it at that for that question. Okay, so question 20, how do satellite-derived air quality measurements complement or differ from ground-based monitoring stations? Are there challenges in reconciling data from satellite observations with ground-based measurement? Absolutely. As I discussed sort of previously, I'll just reiterate a little bit. So how do they complement each other? So the ground-based monitors, they have the main advantage of being right there out on the ground level where people are living or breathing. So what they're measuring is really the best measurement we can get of the local air quality situation where that monitor is. But these monitors are not everywhere. I talked about that a little bit at the beginning, but on a global scale, these monitors are very few and far between. So what the satellite brings is basically the global coverage. We can get, with a polar orbiting satellite, we can get the whole Earth. With a geostationary satellite, we can get, a significant chunk of a hemisphere maybe. So that gives a big global coverage with several limitations. The one being that it's looking at the whole atmospheric column, not just what's happening at the ground level, and the limitations in terms of, especially for the polar orbiting satellites, the time. So it's only maybe taking one observation per day, and maybe less than that if it's blocked by clouds. So reconciling the two together, it's really a question of using the strengths of one to offset the weaknesses of the other. So if you have, for example, a map of variations in the column concentrations from a satellite, that gives you a nice spatial map. And maybe that map covers, a couple of ground-based monitor stations. You use that map, you develop a regression algorithm with the ground-based stations to translate between the column concentration from the satellite to the ground concentration as measured at the stations. You would make some assumptions about how good that relationship is, and you try to test those assumptions, of course, but that gives you a way to translate from the map from the satellite and combine it with the strengths of the ground-based data, which is the accurate measurements of what's actually happening at the ground level, and you get sort of an overall estimate of from both data sources together. Or you bring in a model which tells you a little bit about both. The model has a good spatial coverage as well, and it tells you a little bit about what's happening in the column versus what's happening at the surface level. But the model is, it has its own assumptions that went into creating the model, and it's not always accurate. So by using the satellite data or the ground-based data to sort of nudge that model into better agreement with the actual observations, you get sort of a better estimate overall. So I think, again, I'll leave it at that, but that's sort of a general challenge of how do you use these data sets together in the best possible way. And I've kind of highlighted a little bit of what the strengths and limitations of each data set are. And you kind of have to be a little bit clever and use the strengths of some data sets to overcome the weaknesses of others to get a better overall picture. Question 21, would you recommend combining AOD matrix of AOD Terra and Aqua for better PM2.5 resolution, apart from contrasting low cost and ground measurements? So I think, the first part of this question is combining data from the Aqua and the Terra instruments, and that's actually done. I mentioned it briefly earlier in the MAIAC algorithm, MAIAC, which is the data product we typically recommend for people who are more interested in air quality applications. But yes, it is a combination of the AOD information from the Aqua and Terra. It's still an AOD data product. It's not a PM2.5 data product, but several of the level 4 PM2.5 data products I mentioned do sort of start with the MAIAC AOD data product, and then, as I've discussed several times, combine that with other sources of information to get to the PM2.5 estimate. And then apart from contrasting low cost and ground measurements, I'm not sure what that part of the question is referring to. Yeah, so that's something else. I would say another caveat there. So the Aqua and the Terra satellites are passing over at different times of the day. So it's not necessarily just by combining the data sets together. They are measuring slightly different things because they're happening at different times of the day. So there's a little bit of adjustment that needs to be made with regard to that fact. But so that's what I'll just say about that. Question 22, can LiDAR be used to help fill the gap between 2.2 kilometer and ground monitoring? Yes, so I think with LiDAR, either the space-based LiDAR like the Calypso instrument, or there are ground-based LiDARs as well, which do the same thing, just looking from the ground up. They give a lot of information on the vertical profiles of aerosols in the atmosphere, which is very useful for better understanding the atmospheric system. And in places where that LiDAR information is available, that's definitely a way that we can create that bridge between the column observation from a satellite and what's actually happening at or near to the ground level. The difficulty there is that these LiDARs are only in specific places, so they would only be applicable for a few specific places. I mentioned earlier briefly the Calypso instrument has a very narrow swath width, so even though it's orbiting around the Earth, it's covering a lot of the Earth's surface, but it takes many orbits to get a full coverage of the Earth. I don't recall off the top of my head how many, but it's several orbits. So that's a limitation there, and I think the bridge there as well is sort of a model. So we kind of use the LiDAR information to compare that with our models to make sure that our models are accurate as possible. And then we sort of rely on the model to do its thing in other areas where we don't have these LiDAR observations. We assume that it's performing fairly well in those areas as well. And then we can use the model to tell us about where vertically in the atmosphere these aerosols are. But of course, you know, there are assumptions, there are limitations and uncertainties associated with that. All right, so I think we've come to it seems like we've come to the end of questions in this Q&A document for today, and we're coming pretty close to the end of the allotted time for this training. So we'll wrap it up there. Thank you again for attending, and thank you for all your questions. Again, we'll be going through this Q&A document, finalizing some of our answers, filling in where we need to reach out to other people to get some more specific information on specific things. And then we'll be finalizing the document, as I said, and then posting it to the training webpage in a few days. So thank you again. And yeah, we're looking forward to seeing you again for the final part of our training on September 6th.